Okay, so go to the quantitative problems. I forget which page that's on.
Page 5.
I don't think I have page numbers on the bottoms, do I?
That's after all the multiple.
Yeah, it's after all the multiple choice ones. So just go to the quantitative problems. And let's work through a couple of these, and then I'm going to ask you to do some of these on your own in class here. So we have a pattern of activity that we're always going to use. We create a free body diagram, and then we do a net force equation, and then the net force equation leads us through how to solve the problem. So we have an object that sits on a frictionless surface. It doesn't matter what the object is. And then we're told that a 16 Newton force is applied to the object, and it accelerates at 2 meters per second squared. And we want to know what the mass of the object is. Okay, so if I have my object sitting here and I have some forces on it, what are forces that are acting on this object?
Normal force.
So I've got a normal force. Okay. What else do I have acting on this object?
Gravity.
Gravity. And since the object is not accelerating in the up or down direction, what will the length of that force be compared to the normal force? Okay, so roughly equal. Obviously, if it's close, I'm not going to worry about differences, but if you for some reason put gravity like this, I would have to take some small number of points off for that because it's not correct, right? So a balanced force due to gravity, and then what other forces do I have? I have an applied force. We'll call that FA, applied. Do I have any other forces? Okay, well, we're told that it sits on a frictionless surface, so we're probably not going to have air resistance either. And so one nice thing about these kinds of problems, you've already found out that these problems leave a lot of stuff out, right? There's a lot of implied information that you have to think about, and that's why we go through the process of creating something, so we capture all the information. But if they leave out something that would be required for us to do the problem, in other words, if they don't tell us specifically what the force of air resistance would be, then we can assume that there isn't any. They may or may not tell us that it's a frictionless surface. They may use some code word saying it's smooth. So anyway, this is our free body diagram, okay? So just by looking at this, there's no force opposing the applied force. So I should be able to accelerate here, right? This is just a single force in the forward direction, and there's nothing opposing it. And so in the horizontal direction, I should be able to accelerate. So what am I going to write down next? Force net. And I only have two choices. It's either 0 newtons or MA. What am I going to write down here? MA, it's accelerating, right? Okay. And then, what is the sum of forces? I can only consider forces in the direction of motion. The direction of motion is horizontal, so I can only consider forces in the horizontal motion. And can I have a sum of just one force? Of course I can. Okay, so my only force here, the sum of forces is just force applied. Okay, now that I've got this net force equation, I've told you that the net force equation will always lead you to how to solve the problem. What am I looking for? I'm looking for mass. My practice is to circle what I'm looking for. So how am I going to find mass? I'm just going to do this, right? I'm going to say mass equals FA over A. And what's my applied force? 16 newtons. And my acceleration is 2.0 meters per second squared. So my mass is 8.0 kilograms. Okay, now make sure you understand how these units work. Newtons divided by meters per second squared. There's no kilograms present in that symbol or in that symbol, so how in the world do I get kilograms as an answer? And you have to remember that newtons, since it's a force, and that equals mass times acceleration, the unit newtons is kilogram meters per second squared. Okay, so if I have kilogram meters per second squared divided by meters per second squared, that leaves me with just what? Kilograms, right? So make sure you understand, because this can be really confusing, how I can get kilograms when that's not actually written out there like that for me. Okay. Sports car of mass 1,000 kilograms can accelerate from rest to 27 meters per second in 7 seconds. What is the average forward force on the car? What's the force on the car? Okay? It's a little bit of a different thing here. What are my forces? What are the forces that we're aware of? What's that? Okay, so I've got an applied force. And what are the other two forces? Okay, gravity. That equals mg. And I have a normal force, right? Okay? And what out of all of this is it that we're trying to find?
The newtons forward force.
We're trying to find this, right? So, and yeah, we're trying to find the newtons of that. But I write down net force. And I don't know how to solve this problem, but I'm going to follow my procedure. Am I accelerating, or am I at 0 newtons for a net force? Mass times acceleration equals, the only force I have in that direction is my applied force. So, since this is what I want, I've already got an equation that will tell me what's going on, right? I know what the mass is. I inspect this formula. I know what the mass is. But I have a problem now. I don't have acceleration, do I? So what did I say previously? If I start to work a force problem and I find out that I don't have all the information, I may have to go solve a different type of problem as well. And since I need this acceleration, that type of problem that I have to solve is a motion problem, right? Okay? So I need to solve a motion problem. Now, here's what I hope is going to happen. In the past, when we solve motion problems, we do all this, right? We collect this, and we find out that I have x0 equals 0, and x equals question mark. You go ahead and get your packet out, the problems packet. And then my initial velocity, v0 equals 0 meters per second. and my final velocity is v equals 27 meters per second. So I know that I do this. Okay, so and I also want to find my acceleration. I don't know what that is. Okay, my hope is that you don't need to do that anymore, but if you do need to do that, by all means, gather all your information for this additional motion problem using a motion diagram. But what I'm hoping is now that since you know those 5 formulas that we use for motion problems, or you know that you'll get them on the test, and you know how to access them, right? You know how to access them because you ask a series of questions to do that. You ask if you have time. If I have time, I can't use v squared equals v0 squared plus 2a times x minus x0. If I have acceleration, I can't use x equals x0 plus vt. And then I check to see if I have a final velocity. If I have a final velocity, then I know that I can use one of the formulas that has both velocities in it. And in this case, I know that v equals v0 plus acceleration times time. I have v and I have v0 and I have time, so I can find acceleration. Acceleration equals v divided by t equals 27 meters per second divided by 7 seconds. So if somebody would be so kind as to divide 27 by 7 for me.
3.857.
3.8. So we'll go to 3.9 meters per second squared. Okay, so now all I have to do is go back and plug this in. FA equals 1,000 kilograms times 3.9 meters per second squared equals 3,900 newtons. Okay, was there any point where I had to do any kind of creative thinking here? I just followed my strategy. Okay, I created the net force formula from the free body diagram, and I said, oh, look, I don't have acceleration. I need to solve a motion problem to find acceleration. So I went through that process that you should be entirely familiar with by now. You'll have those 5 equations at your disposal, and you should be able to ask the right questions to lead you through the problem. Oh, look, I got acceleration. Let's go plug that back in. Okay. I want you to try 3. Spend a couple of minutes looking at 3 and see if we can figure that out.
You want us to move on when you finish?
No.
No.
No. So, what's your answer, Blair? What did you get?
I got 16 newtons.
Okay. Did you go through the whole process, or did you just kind of logic it out?
Bit of both.
A bit of both?
Yeah. After I got the numbers, I just logiced it out.
Yeah. So some of these you can figure out in your brain, not too difficult, right? But I'm still going to need you to show me all the work. Now, we've got a little bit of a problem here. Starting from rest, does it say that this object that's accelerating is on a surface? No, it doesn't say that. We can't really assume that. All we know is we've got an object that's doing this, accelerating, because of an applied force. We don't know what the applied force is. We assume that it's not accelerating up or down, but we don't know if there's certainly a force due to gravity on it. So we probably should say that there's a force due to gravity. But if it's a flying object, and let's just speculate a minute. Let's say it is a flying object, and it's not accelerating up or down. What kind of a force would you speculate that needed to balance the force due to gravity to keep it from not accelerating downward? If it's an airplane, what's the force that keeps an airplane in the air? Well, sort of, but there's a special type of air resistance that does it. What do we call the force that keeps an airplane in the air? It's lift. Okay? So we would, and so what happens, and this is just, you don't need to write this down, but if I've got an airplane wing here, that's not a good enough drawing. So if I have an airplane wing here, you know that the airplane wing is curved on the top and more flattened on the bottom, right? Let me just... Okay, so if I'm flying through the air particles are going to go this way over the top, or they're going to go this way underneath of the air, of the wing, right? And if I have an air particle here and an air particle here, but they both need to reach the back of the wing at the same time, right? If I'm flying through the air, this particle and this particle are both going to get to the back end of the wing at the same time. Which of these particles is going to have to go faster, this particle or this particle? Which particle is going to have to go faster to get to the back of the wing at the same time? And why? Why? It's going further, right? This has to go further in the same amount of time as this particle. And what we find out is that in a fluid, if some particles are traveling faster over a surface than other particles, it exerts less air pressure on the top of that wing than there is pressure on the bottom of the wing. As those particles are flying over, these particles down here exert more pressure upward than these particles going over the top exert downward. Because these particles are going faster than these particles. And since the force upward due to air pressure is greater than the force downward due to air pressure, that's called lift. That provides the lift for an airplane wing. Okay? So we have a force in the upward direction balancing this. And for our purposes, I'm just going to say lift because I want to. Okay? But we don't really know what the force is. The problem doesn't tell us that. We just know that there's a balanced force in the upward direction. So I wouldn't really care how you did this, but either just this force applied or added these two forces in some way, I would expect to see on your free body diagram. In any case, it asks what the net force on the object is, and oops, that's force applied. We don't really need to show the sum of forces here, right? Because this is what we're asking for. It's the same. It's the same because the net force is going to equal this force. We don't have a force in the backward direction. And so we're just going to say mass 4.0 kilograms. Oh, wait a minute. We don't have acceleration, do we? But we know how to find acceleration. We do it exactly the same way we did up here, right? V equals V 0 plus AT. V0 drops out. A equals V over T equals 8 meters per second divided by 2.0 seconds equals 4.0 meters per second squared. So multiply that times 4.0 meters per second squared equals 16.0 newtons.
You missed the one.
Is that better?
Yeah. I'm just letting you know.
Thank you. Okay. So if you showed me something similar to this, you would get full credit. But I would need to see this work in order to give you full credit. Okay. Here's one that's a little bit more interesting. And I'll see if you can figure this one out. An anti-tank weapon fires a 3-kilogram rocket which acquires a speed of 50 meters per second after traveling 90 centimeters. And anytime I see centimeters, I immediately convert that to meters. Down a launching tube. Assuming the rocket was accelerated uniformly, what is the force acting on it? Don't worry about the word average force on it. It's just trying to throw an extra word in there to confuse you. So what is the force acting on it? And when it asks that, it's basically saying what is the net force acting on it? So what is the force that's causing it to be accelerated? So see if you can figure this one out. Did you get to? What's that?
We don't have the equation for emotional diagram.
And you don't have it memorized?
Nope. I have two of them memorized, but.
V squared equals V0 squared plus 2a times x minus x0. Right, it's the one that you don't have. V squared equals V0 squared plus 2a times x minus x0, right? You don't have time.
Wait, V squared.
V squared, final velocity squared equals initial velocity squared plus 2a times x minus
Oh,
x0.
I ran on paper.
Dang.
Times x.
Times x minus x0. X0 drops out and V0 drops out, right?
Yes.
I'm not doing
Minus x0.
I ran on.
So you end up with a equals v squared over 2x.
Why? Wait.
No, x, not y. Here.
Okay, here's something I'm going to do for you. You've done several consecutive problems now where we really haven't needed the support of a free body diagram. All we've really done is say that the net force equals mass times acceleration. And that's Newton's second law, right? Force equals mass times acceleration. What I will do for you to eliminate some annoyance is that if all you're doing is just finding out F equals ma, you don't really need to draw a free body diagram. Okay? You don't really need to draw a free body diagram. We didn't really need it here. What's the net force acting on the body? Net force equals ma, right? And you just plug the values in and find the... Okay, so in this case, F net equals ma, right? F equals ma. And be aware that I don't know what the real situation is here. I don't know that this is frictionless. It may be that the applied force has a friction force opposing it. All we're asked to find is what is the net force? What's the result of this force and this force? Okay? We don't know for sure. So why even bother speculating? Let's just say F net equals ma equals 3 kilograms times an O. By the way, we need to find out what the acceleration is. And when you figure out, oh, I need to find out what the acceleration is, your first question is, do I have time? And I don't have time. So I'm going to say v squared equals v0 squared plus 2a times x minus x0. And that drops out because there's no initial velocity, and that drops out because there's no initial position. And so a equals v squared divided by 2x equals 50 meters per second squared over 2 times 0.9 meters. And so 2,500 divided by 1.8, and you got how many newtons? Or what's the acceleration? $50 squared divided by 1.8.
1,388.8 would be.
Okay, that sounds like the acceleration of an artillery shell, doesn't it? That's pretty fast. 1,389 meters per second squared, and 3 times that, it's a little over 4,000 newtons, isn't it? 3 times 1389 is what?
It's,
4,166.
Then 4,167, right?
Yeah.
Okay.
73 2/3.
Okay, so if all we're doing is just finding out F equals ma, I don't really need you to write out the free body diagram, but that's not, I mean, those are easy kinds of problems. That's not what we're going to do most of the time. Huh?
I mean, 2 and 3 were pretty easy.
I think that 4 is not easy.
4 takes a bit more work.
Okay, but once you find out that I need acceleration, once you find out that that's all you really need to do, it's just a motion problem, right?
Yeah.
And your only concern would be, well, do I have the formulas or not? If you had that formula available to you, it wouldn't have been a difficult problem at all, right? Okay, we also need to talk about, we talked about weight last time. Okay, this is another type of a problem that doesn't really need a free body diagram. What is the mass of a person who weighs 110 pounds?
I don't remember the ratio, Dr. Marshall.
So we can say that I want newtons, so I have 110 pounds times, and I want to get rid of pounds, right? So I'm going to put pounds down here. I'm going to put newtons there. When we're talking about weight, we're talking about newtons. So that's not a 16, that's an lb. So 110 pounds. And the ratio is going to be 4.45 newtons for every 1 pound. So somebody multiply 4.45 times 110 pounds.
489.5.
Okay, so that's the first thing I need to do. I need to get this into newtons so I can figure out what the mass is. Now, I know that weight equals force due to gravity, right? We know this. Weight equals force due to gravity. The force due to gravity on my mass is my weight. And I know that that equals mg. Okay, so burn that into your brain. I will expect you to know that the force due to gravity equals mg. And so I want the mass, so mass equals force due to gravity divided by g. And we figured out that this was 489.5 newtons. divided by 9.8 meters per second squared. So all we have to do for this one is divide 489 by 9.8. And somebody's going to tell me that that is what?
About 50.
I know it's about 50.
49.94.
Okay, so 49.9 kilograms.
95.
Huh?
It's 9.5 is a round.
Yeah.
Okay. Okay, so fine. We'll round it up to. Okay. Okay, you guys do 6. It's exactly the same as 5. And then question 7 is a trick question. See if you can figure that out too.
Do you want us to write out the formula for number 6?
I always want you to write out a formula. FG equals mg, right?
Yeah.
Always want you to write out a formula. Because you need to show me the formula and substitution into the formula. You really should know that by now. You know what I'm going to say.
I mean, yes and no. It's just such a simple problem. Like, didn't know if you wanted us to do it.
And you know, my argument would be that if you do it with simple problems, it becomes a lot easier with more difficult problems too. But if you don't do it with simple problems, then
That is fair.
and the only reason I say that is because that's my experience. And when all else fails, do as I say.
Oh my.
Okay, so about 25,
0.51.
25.51.
Yeah.
Okay. So yes, I don't need you to say that weight equals, I just need force due to gravity equals mg, and mass equals force due to gravity over g equals 250 newtons divided by 9.8 meters per second squared equals 25.51 what? Thank you. Okay. So what's the trick for the question in 7? An object has a mass of 60 kilograms on Earth. What is the mass of the object on the surface of the moon where the acceleration due to gravity is only 1/6 that of the Earth? Yeah, go ahead, Beckham.
I divide gravity by 6.
Okay, but that's wrong.
It is?
Yes, because Daxton has the correct answer up here. He still said 60 kilograms. Why is it still 60 kilograms?
Oh, because mass doesn't change.
Mass doesn't change. It's the mass.
So do you have to show anything on that one?
Nope.
So that's just the answer right there.
Yeah. But if you wanted to be especially bright on that, you could say mass doesn't change. But you don't have to. Okay, you can certainly expect me to put one of those on the test.
So just 3 points basically.
Well, it would just be 1 point.
3 points?
Oh, 3 points?
Yeah.
Yeah, I thought you said 3 points.
No.
Keep it mass does not change, it should be extra.
No.
Oh.
It should be extra credit, but mass does not change.
I agree.
Oh, then 8's the same, isn't it?
Not quite.
No, because that's the new movement.
So an object A weighs 40 newtons on Earth, and object B weighs 40 newtons on the moon. The moon's gravity is 1/6 of the Earth's. Compare the masses of the objects.
I think you're just doing some. So you multiply this. The newtons by 1 over that. Push that across the center. Make it. Oh, it's that, so yeah.
They're different objects. So I need your mass. They're different objects.
Wouldn't the mass be the same?
No. The mass is going to be different.
And then the other one is just 40.
Over by mass site. 60 grams equals 500 pounds. 100
So you bake it. I don't know, maybe that's.
Okay, so what's one way that you can do something like this that you're probably using right now are you just actually calculating the mass of both of them?
Yep,
Yes.
that's exactly what I just did.
Okay, so you could calculate the mass of both of these. You could do that. You could say that the force due to gravity on A equals mass A times the acceleration of gravity A, and you could just calculate what the mass of A is, right? You could say that's 40 newtons divided by 9.8 meters per second squared, right? And then you could do the same thing for the moon. Or you could recognize that the mass of A equals force due to gravity on A divided by the acceleration due to gravity of A, and the mass of B equals force of gravity B over the acceleration due to gravity of B. And you could recognize that what they're asking for here, they're saying compare the masses. So one way that I could compare the masses is by dividing them. You know, I could say mass A over mass B. That's one way of comparing them. What do I know about the force due to gravity of each of these things? It's the same, right? 40 newtons and 40 newtons. Okay, so the ratio of the masses is just going to depend on the ratio of the acceleration due to gravity. Okay, so all you would have to say here is mass B is 1/6 of the mass of mass A. Okay, if I said mass B over mass A, that would be 1/6, because the ratio of this to this is 1/6, right? Okay, so you could do that in a simpler way than just, so what if you divide the mass of the thing that you found on Earth by the mass of of the thing that you found on the moon, did you get 6?
Yes.
Okay, so you don't have to go through finding out what the mass of each of these things is. You can recognize that because both of the weights are the same, the acceleration due to gravity is going to be that same 1/6 as what the problem states. So you could just say the mass of the thing on B is going to be 1/6 of the mass, and you wouldn't even have to show me that. But if you wanted to, you could figure out what the actual masses were, and that would prove it as well. They're just trying to get you to think a little bit more about the idea that it's a ratio. You're dealing with a ratio here. If the gravity is 1/6 of Earth's gravity, then the acceleration due to gravity is going to be 1/6 as well. But since you're talking about both of these having the same force, the masses are also going to be 1/6. Okay? So that's all you had to say. Let's stop there. We're going to talk about elevator problems next time. And we'll start a little bit of a lab activity where we go into the elevator and see if what our calculations are actually correct.
Elevator problems, I feel like, are a lot. We did a few last time, did we not?